All right, welcome to week 7 of our Open Agriculture Learning Series. If you've been following these, by hosting this learning series, we're hoping to generate the ongoing discussion so we can identify common barriers and points of collaboration for open agricultural tools, and focusing specifically on monitoring and sharing and creating links between environmental models and modelers. My name is Doran Cox. I'm with FarmHack and Green Start, and excited to be here with Peter Donovan, who's going to be presenting today on the Atlas of Biological Work. But before we get started, maybe if we could have the other folks joining the call to do some quick introductions for us. Maybe Dan, do you want to go?
Yeah, sure. I'm Dan Travis. I'm working with Greg Ostick and others on the PhotoSIC project at Michigan State University.
Dan
Great.
Kane?
Yep, I'm Dan Kane, the other Dan. I also work at Michigan State University doing soil carbon research.
And Mark Easter.
Hi, I'm Mark Easter. I'm at Colorado State University working on greenhouse gas measurement and mitigation methods. I work with Keith Postian and Kevin Brown here at the Natural Resource Ecology Lab.
Terrific. So, Peter, the floor is all yours. Looking forward to your presentation.
Okay, well, thanks. Yeah, I'm Peter Donovan with the Soil Carbon Coalition, and today I'm parked. I'm traveling in my school bus as per usual, and I'm parked next to some friend's house. They have some good internet here, but I think there might be some poultry noises, so don't be alarmed if a rooster comes into my bus and I have to get up and close the door or something like that. So I'd like to talk today about one of our principal projects. The Soil Carbon Coalition principal project to date has been the Soil Carbon Challenge, which is got about 300 baseline plots and about 30 remonitored plots in North America so far. And we're trying to track soil carbon change in some fairly innovative management scenes. And it's largely a producer-funded project, and we're using some fairly strict methods of sampling and analysis, and it's fairly ancient technology in the sense that it's digging holes, taking accurate samples, and getting them analyzed with laboratory devices such as elemental carbon-nitrogen analyzers. And we'd like to raise the visibility of what I call biological work. I'm not too fond of that term, but it's what I'm using at the moment. And I'd like to start by giving a bit of background, and then I'll be getting into the nitty-gritty of what we're doing with Google Earth Engine and a few other tools. And the purpose of this presentation is to, I realize that many of us are working on very different things with different purposes and different angles, and I don't expect that to change, but I do think that by learning more about what we're doing, we can add value to each other's work. And also, today I'm looking for suggestions, advice, connections, and all those kinds of things. So I'd like to start by starting a short 12-slide PowerPoint presentation. And I'll start. Does everybody see that, or is it coming on?
I can see it.
Yep, me too.
Yeah, me too.
Okay. Well, there's a lot of perceptions, there's a lot of angles that people view the situation in, and there's a lot of funding streams, and there's not a lot of sometimes coordination between people working on these various issues and problems. And I think most of us realize that in order to address these problems, we need big changes. These are huge flows of matter and energy that we're dealing with all these issues on this elephant here. And as a friend of mine says, Don Campbell in Canada, if we want to make small changes, we change how we do things. We develop new strategies, we do different kinds of things. But if we want to make big changes, we have to change how we see things. And this is what our Soil Carbon Challenge work and the Atlas work is devoted to, is to change how we see things. And to make this easily available for people to at citizen levels of usability. These big changes in the flows of matter and energy, for example, require work. And by work, I mean force times distance. In other words, we're not going to make these big changes by technical fixes or mere policy shifts. These are needed, but they're not sufficient. And I'm pretty emphatic about this work, force times distance, and we'll get into the background of this a little bit here. But how do we see things? And I think we see things in terms of usually the issues that we're working on, the problems that we're dealing with. We're typically in a managing against scenario, where we're trying to manage against one or more of these problems. And of course, and this is also how we collect data and how we map things. This is how we see things. For example, you all know the Keeling curve of rising carbon dioxide. We map extinctions, we map pollution, we map health problems, food security issues. We map and collect data on economies and communities, all these different issues. And we do a lot of research and prediction based upon this data and the mapping and so forth. And it's all pretty much based on the parts. So we have very much of a fragmentation going on. And it's been going on for a long time, a couple hundred years at least. And as Gregory Bateson remarked, that the way nature works and the way humans think, there's a real disconnect between that. And this is the way I see things. We spend probably billions of dollars mapping species, problems, practices, land cover, conservation status, pollution issues, all of the problems. And biological work, we don't usually map it. In a couple of situations in agriculture we do, but the power of photosynthesis, for example, is usually not mapped at a local scale, or if it is, it's not factored into our decision making or our policy. And you know, you've heard the old story about the guy looking for his car keys in the alley. He dropped his car keys in the alley, but he's looking for them under the street light because that's where he can see. And that's where our knowledge, our data systems, our mapping is illuminating all these specific issues. And largely the work of the biosphere is in the shadows still. Now, work is abstract. You see its results, and change over time is how we detect it. And photosynthesis is the most powerful and creative planetary force. And a quick resume of that, just to make sure we have the right perspective or broad enough context on this. It uses only a sliver of incoming sunlight, but the chemistry that photosynthesis does has transformed our planet. It's given us a rich oxygen atmosphere, which in turn forms stratospheric ozone, which protects water vapor from disassociation by ultraviolet light. Mars probably lost its water because of the lack of an ozone shield, a stratospheric ozone shield. A lot of evidence that there was lots of water on Mars at one point, at some point in the distant past. But our ozone shield protects us from losing water because of the photodissociation of hydrogen and oxygen, and the hydrogen escapes the gravitational field. 10%, if you lose your hydrogen, you lose your water. 10% of our surface rocks are the residues of living organisms, and our atmosphere, the composition of our atmosphere, and of course our soils are largely the product of the metabolisms and choices of living organisms, cumulatively over billions of years. So that's why I call photosynthesis, which drives the carbon cycle, which influences the water cycle greatly, is the most powerful and creative planetary force. And we're part of this cycle. Our behavior, our beliefs, our consciousness, our self-awareness are all derived from photosynthesis. And although we live in a world that is pretty much closed for matter on our planet, we don't lose a lot of material, we don't gain a lot of material. We're in a hugely open system for energy. Sun, 5,800 K at its surface, Earth, about 287 K, receiving an enormous flux of visible light and, fairly short-wave radiations from the sun. And we're losing that energy in terms of outgoing long-wave radiation to space. So we're in a tremendous distance of energy. We're in an open system with enormous flows of energy through it. And although it may seem to many people that we're in a fairly static system, like a still mountain lake, for example, we can move that if we thrash our arms, do cannonballs, get an outboard motor, do a whole bunch of donuts. We can make waves, but time will erase our work. The thing is hard to move, hard to shift. But a fast-moving stream, on the other hand, a non-equilibrium system, putting a rock or a log in that has tremendous leverage if it's done right. And over time, you co-create different results with the energy of that stream. But we're not gifted in knowing initially how to do that. What it takes to learn how to move a stream with a few boulders and rocks and so forth is a feedback process. And I think we have a tremendous learning opportunity here. And as Lovelock said, there are no rules, just consequences to our dealings with the natural world. I think we're in a multi-dimensional shift now. We have increasing awareness that we're in very complex situations where mechanical or linear or reductionist decision-making doesn't do very well. And that we also realize that the power of biology is much larger than that of, say, our fossil fuel energy use, or even all of our industrial energy combined. Photosynthesis alone is about 130 trillion watts worldwide, globally, including the ocean. By contrast, our industrial energy is only about 16 trillion watts, about an eighth of that. And it cannot do many things, such as build or maintain soil aggregates. We can change the rate of destruction by, say, going to no-till types of agriculture, but we cannot literally build aggregates with fossil fuels. We rely on photosynthesis to do that, build a soil aggregate. This is a very brief outline of the levels of solar energy reaching the Earth, and very quickly we have, you know, about 1,800 horsepower per acre coming in at the top of the atmosphere. A third of that or so is reflected by ice, snow, clouds, and dust, some atmospheric absorption. About 160 watts per square meter, or about 1,200 horsepower per acre, is absorbed as heat at the surface, primarily by our dark oceans, and that drives winds and currents. Water cycling is responsible for about the other third, which evaporates water and drives the water cycle, which is a huge heat engine, if you will. By contrast, photosynthesis is a tiny percentage of that. Most of the light energy that strikes a leaf is reflected, it's absorbed as heat, or it evaporates water. Very little of it actually goes into the photosynthetic process. But what does is very critical, because it as I mentioned, it transforms the whole planet by splitting water and releasing oxygen. Of course, we have the atmosphere, and we have soils. We have the enormous complexity of living organisms that continue to transform our planet. We'll go down to behavior, consciousness, and beliefs, and finally, there are many forks in this pathway, if you will, but self-awareness may be the final step. And there's enormous leverage from the bottom to the top here, because we're not in an equilibrium system. Human consciousness, beliefs, or the lack of self-awareness, if you will, has led us to inadvertently change the albedo of the Earth in terms of the reflectivity and the surface heat absorption, the way the water cycle works, the way the carbon cycle works, the way behavior of all these organisms, everything like that, and is beginning to change our consciousness and our beliefs. So there's an enormous leverage from the very small uses of solar energy to the larger ones. I want to talk a little bit about the importance of monitoring what I call the middle distance here. NASA and so forth, we have pretty good monitoring of atmospheric carbon dioxide levels and surface heat absorption. We have a fairly good monitoring of the big things. But what we do on our 40 or 160 or 1,000 acres is not likely to make very much immediate change in those large things. So they're too distant to be of practical as feedback to our management of our properties or even policy work. By the same token, if we monitor what we do every day, which most of us do, we believe we do good things, and maybe choose paper over plastic, or whatever the reverse is, or whatever the different things that we do, different choices. We move the cows every day, whatever we do. It's easy to deceive ourselves about the results of our actions, or to become politically correct or whatever it is without understanding the results. And that's why the water cycle and the carbon cycle, I think, are critical to our monitoring, because they're at a scale and a time scale where we can actually see some effects in 3, 5, 10, 15 years, and also at the scale of, say, 40, 100, 1,000 acres. And so that's where I think the critical monitoring need is at that middle distance on the 7 generations of sunlight here. And we need to learn what works as a society. As I said, we're in a shift from realizing that that biological power has much, much more influence, and if we're going to make massive changes in the flows of carbon, water, nitrogen, phosphorus, all these things, we need big power, and that's where the power on the left, the 130 trillion watts, multiplied dozens of times by its effect on the water cycle. Soil moisture is probably the principal capture of solar energy by biology. And our puny little technology on the right is often in the way, and we need to work with this. We need the learning opportunity. We need feedback. So what we're trying to do here is expand our soil carbon challenge, which is an open monitoring effort, as I said, primarily funded by producers, but with some additional support from a few foundations. And as I've said, the critical thing about monitoring the work of the biosphere, which is what is the circle of life, it's what makes the world go round in almost every way save the literal spin, is this enormous creative power of photosynthesis. Here's an example of the open kind of mapping that we're doing for the Soil Carbon Challenge. These are spectacular figures, I think, from Saskatchewan, southeast Saskatchewan. In 3 years, carbon has increased in all layers. We have a slight decrease in the bottom, but it's hardly to the point of measurement distinction. 6 out of 6 farms showed large increases in 2 out of 3 or 3 out of the 3 layers that we sampled. And this is in 3 years with planned grazing, holistic management type grazing, and fairly high stock density. No other inputs really, no fertilizer, no chemicals. And we're starting to use Google's Earth Engine, which is mounting satellite imagery for computation purposes on Google's platform of servers and so forth. And here's an example. People have been able to do this kind of thing for quite a while with remote sensing processing software, but Google's Earth Engine is very interesting because it's moving this from the specialist experts out to a wider audience. And we think this is going to be a very big thing in terms of changing how we see things. In other words, we're actually able to look at energy flow, and normalized difference vegetation index is one proxy for this. The advantage of the satellites is they go over every 2 weeks, and regardless of weather conditions or whether the wind is blowing too hard to fly something or whatever. And plus the record goes back, in this case, to 1984 when Landsat 5 was launched. And here I have Gabe Brown's place in North Dakota near Bismarck. It's the small red rectangle in the center, and then a fairly arbitrarily chosen neighborhood in the blue around him. And by the way, he does manage some of the area between the red and the blue. I'm not sure exactly what, but these are the boundaries I have. I was able to run year-long normalized difference vegetation index composites from the surface reflectance products that are now available from NASA and USGS via Google Earth Engine. And these are, as I said, calibrated surface reflectance products. So they account for the zenith angle of the sun, the atmospheric haze conditions, and so forth, and get a better picture of the various wavelengths of light that are actually being reflected from the surface. And this is, we're using some cloud filtering algorithms here as well. Here's the colors are reversed. The blue is the Brown Ranch, the red is the neighborhood. And I know something about the management of this place. They started using no-till methods of farming around 1991 or 92, and they're not really beating their neighborhood in any real sense in terms of the amount of sunlight energy that they're capturing with plants, which is the input to soil health. It's not the whole story, but it's the input. And you know, they're doing a little bit better on the higher production years than the neighborhood. And around 2004 or so, Gabe Brown started a strategy of multi-species cover cropping. And from 2004 on, he beats the neighborhood by a significant margin every year in terms of the sunlight energy captured by plants. And this has resulted in a, he uses no nitrogen fertilizer these days, and his herbicide use and pesticide use has gone down by huge margins. And anyway, this is what's possible to recognize with this kind of view of energy flow. And I'd like to talk a little bit about open data. I think it's crucial because we need to learn how to do this not only as individual land managers and neighbors sharing data from neighbors perhaps and learning from that, but as watersheds, as regions, as states, counties, and much larger units in terms of what kind of policy are we really going to be developing, and how can we test that policy for what works? Because as I said, we're not born knowing how to do this. We need to learn, and there's a big learning opportunity for it. To measure work, it takes usually some kind of time series observations. And in order to be Can people hear me?
Yes.
We can hear you.
Okay.
Dee Dee can't, but I think the rest of us are getting it.
Yes.
Okay. Okay. Repeatable monitoring has a number of incentives, if you will. If you want it to be repeatable, it can't be too complicated because the funding may not be there forever and ever. If you're using $50,000 technology, it may not be as repeatable as we'd like. And one of the things that we're doing for the bottom part of our Atlas of Biological Work, for the top, we're going to obviously use Earth Engine. We'd like to develop a product like the Forest Cover Change Map that is easily viewable, shows change over time, differences between areas on how that works, and also is very easily shareable and can be mashed up with other forms of data and so forth, as the Global Forest Watch people have made that with the Global Forest Cover Change Map that was also developed with Google Earth Engine by University of Maryland, Google, and others. Biological work is a little tricky because we're not used to seeing it. As I mentioned, the work of the biosphere is quiet, gradual, spread out. It's not like a diesel engine. And though most of us realize that a tree root can push up a concrete sidewalk, the work, force times distance, because its chemical energy is often a little bit obscure and not recognized for the most powerful and creative force that it really is. And there's a lot of ways to measure this work. We think soil carbon change is fundamental. Also, photosynthesis is fundamental. The function of the water cycle is fundamental, although that's trickier to measure in a lot of cases. One of the reasons we measure soil carbon rather than soil water is that it's easier. It's easier to get a fairly accurate reading at one time, whereas measuring soil water it has to be a continuous process pretty much, and it depends on the pressure and so forth. The other part, measuring infiltration through the surface, I think there's enormous potential for citizen science type things to do that. Schools, community groups of all kinds, individuals, and we're working on a digital infrastructure that will make that very easy. And one of the things about open data is that I think it requires a different kind of structure than most of our data. And I can show this. Here we have the design of most of our relational database systems, rows and columns and relational indexes and so forth. What that does is it tends to keep our data in silos and prevent new things from coming in. It's very hard to change the scheme of one of these things once you build it. Or it may take lots of approvals, and there could be power struggles and lots of sunk costs with that. We're going to use a graph database such as Neo4j for all information that's the advantage of this is it's doesn't have strongly typed data. If we want to add a new kind of data to it, it's very easy to do. Graph databases, nodes, and relationships, and that's more the way the real world works. It's very easy to cross domains here in terms of you can store data about people, about management, about bulk density measurements, about any kind of measurement or any kind of thing you might want to store, and it can be related to everything else by relationships. And as I said, if you want to add something new, it's very easy to do that. So that's why we're choosing a graph database over a traditional type database or a structured query language database, because we want to have the flexibility of putting new types of data that may not be strongly typed and connecting that with the whole thing. Repeatable time series graph databases are very well adapted to time series arrangement of observations, for example. There's a lot of incentives for data to remain hidden. There's the database thing like we've talked about. There's a lot of conventional wisdom, a lot of institutional traditions, a lot of reward systems and agendas that institutions and organizations sometimes have that privilege the power of experts. And I think there's an opportunity to make this kind of awareness, this difference of how we see things, much more participatory and open, and I think it'll have network effects once we get it going. So some of the things that we'd like to be able to measure are water infiltration, soil carbon change, photosynthesis and change thereof, and stream flow changes. The U.S. Geological Survey in the United States has an enormous database there that can be made much more usable, plugged in, user-friendly. And I think it'll add value to a lot of the work of watershed groups, community groups trying to deal with all these problems that we saw in the beginning, the stripes on the elephant, if you will. You know, desertification, flooding, drought, climate change, scarcity conflicts, weeds, pests, you name it. There's an increasing realization that dealt as, if we deal with those, managing against what we don't want as individual problems, we'll be continuing to spend trillions and without perhaps the kinds of results that we need. And that it is by understanding, learning to work with this power of the biosphere, photosynthesis and water cycling, that we can outgrow the problems, if you will, or at least make our situation more resilient and structured to learn what works. Anyway, this is just a brief overview of our Atlas of Biological Work project, which is an extension of our Soil Carbon Challenge. And I'm looking for advice, suggestions, connections, anything that people might be able to contribute. As I said, I think this kind of thing, being open, citizen usable, will have the ability to add value to a lot of the work of a lot of different people, but probably in different ways. Anyway, I'm done. So if anybody wants to comment or give us suggestions, that'd be great.
Well, thanks so much, Peter. Before we get too far into other questions, we've got the standard questions that we ask all of our presenters, which are first, what are your barriers, and what particularly about collaboration do you think is going to be helpful to overcome them? And then also, how do you relate your project specifically to farmers and regenerative agriculture?
Okay, the barriers, as I mentioned, there's a lot of incentive systems that tend to reward privacy of data or lack of sharing, and a lot of these are academic traditions. Soil labs don't share their data. NRCS does not has a policy of not sharing personally identifiable information. So even though they do a lot of soil sampling and inventory stuff, that data is not really public in the sense of being geolocated. We can't tell where it is. So the reward systems are also for individual accomplishment. You know, can we publish a paper on this? And lots of research projects that deal with soil carbon, for example, in my opinion, don't constitute repeatable monitoring. For one thing, they're typically chronosequences, you know, fence line contrast kind of things. They're not change over time necessarily in one place, like we're doing with the Soil Carbon Challenge. And it's not that hard to do it, but I think I think you have to see things a little differently in order to want to do this, want to be a part of this. And see the other questions, Dorn.
Oh, just specifically relating it to farmers and regenerative agriculture.
Yeah, okay. One more question, one more answer to the previous question. One of the barriers is that I'm looking for expertise in designing apps that work with graph databases, for example, mobile apps, and that's fairly rare. Not too many people know how to do that. They're mostly interested in working with relational database systems. And so that's one of the barriers. There's a lot of expertise on Earth Engine that help us do this, but we're looking for more. Most of the people working on this remote sensing stuff are looking at classifying land cover. They're looking at object identification. They're looking at deforestation. You know, all the problems on the elephant that you might see, they're looking at those things. But I think most of them are missing the big picture. How is sunlight being captured biologically, and how does it change? And how is it changing over time? Can we discover who's learning how to do this? And it might be surprising. We have lots of advocacy, lots of theories and stuff, but not a whole lot of monitoring about what's actually working. In terms of regenerative agriculture, I think it has a high relationship in that, as I said, there's a lot of rhetoric out there, there's a lot of advocacy, my method's better than yours, that kind of thing, and not very much monitoring. And I think this kind of feedback is at a time scale that's relevant to management. The people that I've done this for that showed soil carbon change have felt very empowered by knowing that their management is building soil carbon even in California's drought, for example. We're seeing in one plot I did down there, saw 11% increases in some layers of carbon during a almost unprecedented drought in California.
Well, and just to add to your point there, Peter, I think one of the barriers you identified was identifying those, what we talked about at the Pacinas gathering was bright spots, is finding those instances on a large geographic scale that are working and then starting to connect those through social systems, so that farmers who are developing things that have been measured to work can find other folks who are similarly successful. So I really see that, when you look at Gabe's property there and you hear him talk about it, and then you can actually get the satellite data and start to link those together, I think that starts to tell a powerful story. And again, to move people, well, somebody said we need stories to move people and we need numbers to move money. So that was, I think, that was helpful. That graphic in particular I found quite helpful. Other folks would like to jump in?
Yeah, Peter, thanks for presenting, and I like the kind of perspective you presented and how that kind of informs what we're doing. I agree a lot about your points that if we want to be able to kind of build this type of database, one of the important things is citizen usable tools. So I'm just wondering if you could comment on that, and in terms of, since you've sort of already done a lot of this work with farmers, what types of tools, what types of data are they looking for? And what do you see as the best options to develop for them?
Well, the ones I'm working with are very interested, for quite a variety of reasons, in soil carbon, and because I think a lot of the people that I have been working with realize that while carbon is only a few percent of the soil mass, it's responsible, as Chris Nichols says, for 90% or more of soil function, especially changes thereof. And some of these people have been interested in the possibility of carbon markets or carbon credits. We're not directly dealing with those because in some ways I think they're based upon some kind of strange thinking that comes from managing against what we don't want, in other words, fossil fuel emissions, rather than managing for what we do want, which is increased soil productivity and water holding capacity, which will have a side effect, if you will, on climate if it's on a big enough scale, but it has local benefits. Some of the other things, whenever I show Earth Engine stuff to farmers and ranchers, they're very interested in that because that's a view that they have. I'm talking long-term composites, year-long or more. They see, well, this part of their pasture is, they always thought that was more productive, and yes, they see the evidence that it maybe is. They can see their grazing plan unfold. I think that it's sometimes difficult to see the economic benefit of raising more forage, but that's apparent to many people. And one of the measurements that I think has enormous potential is an economic one, and people are increasingly clued into this. People who've been through the Ranching for Profit course, for example, know that the value of being able to say, well, my pounds of gain in beef, for example, per acre have been steadily increasing, even though rainfall is sometimes not. Or bushels, if you're a corn grower, bushels per inch of rainfall. Those are key factors in gauging your capture of solar energy, which is the free stuff, not buying your crop with fertilizers and so forth. And people like Gabe have been very effective, I think, at pointing this out. We don't know everything that works, and I think the satellite view has an enormous potential of discovering things that we didn't realize were making a difference before. If we discover those, then we can tease out maybe what was happening here, what was contributing to these successes. And most of us are interested in learning from success rather than being criticized for failure or being regulated by other people. So I think the economic measures have quite a potential to look at the whole, and I think the whole in this case is very specific. It's the capture of sunlight energy, the most powerful and creative planetary force. I don't think it's just a hippie or new age word. It's work, force times distance, and can be quantified and doesn't necessarily need to be, but that's how we can test policy. For example, CRP. Again, running into lack of open data here. There's no map that shows all the CRP ground in the United States. So we can't test it for photosynthetic activity because these things are concealed. And our policy and our monitoring are in separate silos.
So, and Peter, we're talking mostly, I believe, about tools that are hosted online and mobile tools. Maybe you could talk a little bit about some of the initiatives or some of the tools that are currently inspiring or that you're basing your future work on, or sort of some vision around how you see those tools being used and who's in that community.
Well, I've only gotten into this a very little bit, Dorn. I've started to use Open Data Kit, which is an open source mobile app for devices only. It's fairly old. It was developed by the University of Washington in cooperation with Google some years ago, and you can design your own data forms. Excuse me. And you can work offline, off-network connection, which those I think characteristics are both essential. If you have to use somebody else's data form, it may not work for your situation, or it may not be appealing for you to do that in a situation. And that's one of the main reasons why I think we're going to a graph database for a repository, if you will, because it can accept and organize weakly typed data and data whose schema may be changing with time. Whereas if we have a relational database system, we're usually locked into some sort of schema, and things don't fit that. Right. But I don't see a lot of development in that area, and that's one of the things we're looking for. Who's building off-network devices that sync with a graph database? Some of this, it's not important to have it on a mobile device. For example, the soil sampling and analysis that I do, that's all, laboratory stuff done afterwards. It's not important that it have to be on a mobile. But I think for getting citizen science people out there, I think mobile apps are very important, because otherwise you have some nasty homework of collecting field notes and transcribing them into some sort of digital format and posting them and so forth. It's really nasty. It can get overwhelming, and that's part of data being open and having a learning system as a society. If we keep things in shoeboxes, for example, or Excel files in our own hard drives or whatever, that stuff is not available to be used or mashed up with anything else, so that people might increase learning. It's also possible to go the other way and get too much data to where it's over-parameterized. We don't know what to do with all this data. It's overwhelming, and it becomes irrelevant that way. I think it's very important to concentrate on a few specifics that are understandable by a fairly wide range of people. And so there's a teaching and facilitation part of that too, that I think needs to happen face-to-face on the land.
Yeah, I think there's something to be said for the fact that some of the tools to actually generate the numbers can and maybe should, at this point in time, remain old-fashioned. Kind of nothing can beat the accuracy of a soil sample that you run through an elemental analyzer. But I like the idea of then delivering that data and contextualizing it for the producer or for whomever it is in a way that's either kind of through a mobile app or through something that kind of is more something that puts it in the context of their farm and their kind of in a map, something that translates for usable information.
Dan, I think you were breaking up there a little bit on that last bit.
Oh no.
I know where you were going.
Do I need to? Yeah.
Creating actionable data. Yes.
Yes. Yeah.
Yeah.
Because there seems to be there are different elements of this. One is handling the data, and then the other is sort of the social aspect of what do you do with it and communicating with the other members within the network, which is partly exchanging data, but often it's more, I think it's also about making personal connections and exchanging the stories behind that data, and creating social networks about land management. And I didn't know if there are sort of, Peter, whether there are models that you were looking at particularly. I know you mentioned iNaturalist at one point, whether there are other sort of communities that you've been inspired by.
Well, for sure, iNaturalist, and which is a species identification app, and where that's often used is in what they call bioblitzes, where crowds of people go out to identify species, and that's I think a very good social model for excuse me, understanding biological work too.
So the BioBlitz as a social in-person event coordinated with a larger internet-based network.
Right, and iNaturalist is great because it makes that sort of thing easy, and easy to do as a group or as an individual, and I think that's the key. We need to be able to make these things easy. Right now, it's not easy to monitor biological work.
Well,
people don't know how to do it. The satellite stuff is very difficult. There's lots of barriers to changing the way we see things, if you will. And some of these can be eased, I think, with technology.
Well, I think that's a perfect cue to get some comments from Dan, if he's willing to jump in here. Oh, Dan Teravest. Oh. Well, maybe he's on mute. Anyway, I was just going to mention that seems to be a good overlap with what they're working on with the PhotoSync project as well, with working towards both the on-the-ground measurement linked with some of what you're looking at from the satellite imagery, and being conducive to some of the BioBlitz kind of social gatherings. That's what we actually tested that out. I believe it was last weekend at our iFarm event. We had one of the PhotoSync devices, and a number of us all went out into the field trying a number of different things. And I could really see being able to start to put that into a larger context. In our case, we were looking at historical aerial imagery, and we don't have enough data to do the kind of NDVI that you're talking about on these smaller plots. But I think the template was really there. We're seeing hints of that sort of moving into practice.
Mm-hmm. Yeah, there's an enormous potential for, I think, uniting sort of on the ground observations with the big picture stuff, either from stream flow from the USGS or satellite vegetation indices, for example. And there's a real need for that too. It's partly, as you said, Norm, putting it in context.
Right. And making it part of the social sort of fabric of our land management. Well, we're right about at 4 o'clock, so I just want to open it up for any last questions before we thank Peter for this presentation today.
And I also want to say that although Abe couldn't be here today, he's contributed a lot to the thinking and ideas and the work that we're putting forward here.
Yeah, I don't have a question, but just a comment that it's thanks again for the presentation, Peter, and I'm glad you're part of this group because it feels like what you guys are doing with the Soil Carbon Challenge and the coalition you're building could benefit from, for sure, from some of the people who are working more directly on the hardware side of it. But you have this kind of network and this project and this coalition set up, so hopefully we can kind of make that, I don't know, marriage happen.
Yeah, we're very interested in working with lots of people on the Atlas projects. You know, as I said, it's open data at various different levels, and mesh-up platforms will definitely be part of this. So how can we connect the dots, put this in context that'll help people learn how to work in alignment with this powerful and creative planetary force.
Well, thank you so much, Peter. Really enjoyed today's presentation, and look forward to our next presentation next week, which will be with Public Laboratory, with Jeffrey Warren presenting on their work, which has a lot to do with this, both the in-person tools or on-the-ground monitoring citizen science tools, as well as trying to create some of this context that you're talking about. So, thank you very much, Peter, and hope to see you all next week.
Okay, thanks, Dorn. Thanks, Dan. Thanks, Greg, or both Dans. And
Great.
All right.